Good afternoon, everybody. I feel today I can offer you two choices, white slides or pink slides. So who wants to see white slides? And who wants to see pink slides? All right, that's half and half. So just give these guys a moment to figure that out. I think I have to stand very still and not touch anything.
Yeah, I mean, this should be fine. It's just try not to hit that if you want.
All right, I'll be all right. Okay. You're recording the video output as well? So, okay, so it will matter if it goes wrong.
It'll match up.
Okay. All right, thank you very much all for coming here today. My name is Craig Box. I lead the developer advocacy teams for Kubernetes and Istio on Google Cloud, based in London. So my job is traveling the world and talking to people about the open source projects that we've built, our cloud products that were built on top of them, and getting feedback from people about what they like and what they would like to see changed. And what I want to talk about today is the Istio project, and specifically why Istio was so compelling to customers that they would use it in production 1 month after we released it as open source, along with IBM. We launched Istio, and we know of customers who were using version 0.2. So you have to be very brave to want to use something so young, but it must solve a real problem that people have. And it's important to know what those problems are so we can see if we can apply them to your business. Now, the most common use case for something like Istio is when you're looking at moving a monolithic application to microservices. Monolithic applications used to just be the only way we would build software. It was fantastic because we would write everything in one process, and so we knew that it all worked. We compiled everything together. You could call any function, so some of those modules there just sort of call each other around in a circle, but that's okay. There are downsides to this. You have to write the whole thing in one programming language. It's hard to test those modules independently, especially when they can be called around in that order. You can't redeploy only part of this. You have to take the entire application and redeploy it all at once. And because of that, you can only move as fast as the slowest person in your release cycle. You have to synchronize your teams together, find out when they are ready to release, and businesses with applications like this have a person called the release manager, and that person says no to everybody. And then 6 months' time, they say, okay, we can release now, and if you miss that train, then you have to wait a long time to get on the next one. So we moved to microservices in order to try and solve these problems. We are solving business problems here, and we're using a technical means to do this. We talk about decomposing a monolith. So we remove the dependencies. We make it so things only call each other in a straight line. We define interfaces between these modules so that you expose an API and you publish that as a contract. So you know people who call you are going to be able to call you regardless of what version of that software you've released. And we can update these independently as long as we keep to that API contract. That's a summary of the reasoning behind this. Ultimately, it's about organizational issues. Jeff Bezos, the founder of Amazon, talks about 2 pizza teams. You want a team of people that is small, you can take 2 pizzas to feed them. And that's the number of people that should work on any individual service. So we can get that velocity, so they can deploy their software faster. So we can decouple these services from one another. And then people can use whatever software makes sense. If there's part of their environment that makes sense to use in Erlang or Haskell or something, we can do this. We don't need to tie everything to the same language or have to run on the JVM, for example. We're decreasing how much a single person needs to know so they can care about the things that matter to them, and then they know the services that they have to interact with. And hopefully something that goes wrong somewhere else in that graph won't affect them. So that's fantastic, great, we've decomposed our monolith, we're moving faster, we can test easier, we have these abstractions, and we can scale our services. So the question is, what was the cost? What have we lost here? inside our monolithic process, we were the caller and we were the destination. So we knew that it was reliable because we were both ends running in that same process. Now that call goes over a network. The network may be insecure. The latency on the network might be high, or it might change over time as the network is saturated. You have to worry about access control. Previously, you were both the caller and the destination. Now we are having to call someone and verify who we are all the way through. And we used to debug these processes by attaching a debugger to it and stepping through and looking at what happened. Now we have to say, well, I'm not really sure what we do here. Like how can we debug these things? There are some fixes that we can do here. If we're worried about service A calling service B, we can say, try again, maybe wait a while longer if the first one fails and try again, exponential back off. And then we can add some headers to our calls to say, it's printf debugging basically. I started, I called this other service, I responded, like where we got through, and you can look through a trail of logs from many different applications to figure this out. Then you can add security and authentication. You can build this into each application, but because we have taken these modules and possibly written them in different languages, now we say, I have to have a library that works in Java and in Haskell and in Python and C. So ultimately, these microservices that are designed to be small aren't micro anymore. We have to worry about all of these things which are not generating value for the business. Even once we have those things running, when we want to move to scale, this is hard. We used to give software out on disks to one person at a time. Now we are serving software predominantly to millions of concurrent users over the network. So at the bottom of this, we need to have some sort of metrics. We need to be able to say, what is it that our application is doing? And then we can monitor and alert on those. We want to be able to handle the encryption and identity, both from people calling outside and inside the network, and then do things like rotation, identity, make sure that only services that are allowed to call each other can do so. We need to handle traffic management. We want to be able to do deployments of new services. If we deploy a new service, we'd like to send a small portion of the traffic to it until we know it's successful. And if a service fails, we might say we don't want to keep calling that service. We want to gracefully degrade. If we display a web page and it has a little widget that displays the weather, if the weather widget is broken, you can still display the rest of the page okay. You don't need to wait until that gets built. So there are all of these things that we want to do. And so the question is, how does your startup or the DevOps organization in your company deal with this? So this is a startup. There's about 40 people, I guess, working here at the time. And ultimately, when we think of what we've developed internally is to, since we were that size, we talk about the culture of site reliability engineering, or SRE, and we look at the way that we have developed services, microservices, or a larger scale. So you've heard a lot in the last couple of days about observability. Observability starts with monitoring. Ultimately, we can think of this as a food group pyramid or Maslow's hierarchy pyramid. And we can say, you need monitoring before anything else. And what we've done is we've taken monitoring here and saying, well, let's break monitoring down. What should you be monitoring for microservices? So we call these four the golden signals. These are the things that you need to fundamentally know about traffic on your microservices environment. Traffic is actually the first one. So that's the volume of requests, so requests per second coming into your service. Then once you know that number, you can see the number of errors. Knowing the number of errors alone isn't good enough, because if you have 100 errors, is that a lot? If you have 100 requests, then 100 errors is a lot. But if you have millions upon millions of requests, then that's okay, that's a small percentage. And that might be within your acceptable boundaries. So when we move further up, again, we're starting to say it's not so much we need sleep and so on, it's the nice to have things. So we start looking at latency. Customers expect apps to be fast. So we need to make them fast, and we need to measure not just the average of requests, but the slowest requests. We talk about the percentiles, 99th percentile, 99.9, the tail latency. What is it that the slowest people are seeing? Because ultimately that will dictate when things get slow throughout a chain of calls to microservices. And then saturation will be something that matters custom to you and your workload. So it might be I'm overloading a CPU, or I'm running out of memory, or something that's custom to you. But that is the 4 signals that we recommend you monitor. There's a great quote from an early professor in computer science who says all problems can be solved by another level of indirection. So how do we monitor all of these things? Well, we use a proxy server. Traditionally, people will think of a proxy server something like this. You have a bunch of front-end services and a bunch of back-end services, and for these to call into that, they call into this mid-proxy that sits between them. It's able to do some authorization, some traffic routing, or a load balancer, for example. And you have a proxy per certain number. So if you have 10 replicas, you might have 1 proxy, and if you scale up, you'll need to scale that as well. So we moved very quickly inside Google to what we call the sidecar model. What we do here is we take one proxy server, a smaller one, and we deploy it along with every backend service. So we wrap these things up and deploy them together, which means we don't need to make any changes to the code. We basically just intercept the traffic that's going to hit that service through the proxy. And now we can transparently collect that telemetry. We don't need to make any changes to the service. We can use that as the way we do security for these applications, so it can terminate our TLS services. And because they're distributed, we have one tied with every backend. We're getting rid of the single point of failure of that single proxy server. So we gain distributed load balancing. You end up with something like this. If the front-end service wants to talk to the payment service, it just calls out, it looks up the hostname payments, and it connects out to that. It is transparently intercepted by a proxy on the way out, and then at the payment service, which can make decisions on whether or not to allow that traffic. But it doesn't know, the front-end service doesn't know, it just calls out to payments, and it just works from its perspective. That gives us a lot of flexibility here. So the traffic into our workloads being intercepted means we can do things like look at quota. Is there too many requests being made to this service for that particular user? We can take authentication and authorization decisions and move them out of your application. So your developers don't need to keep rewriting that same code. And we can do the same thing on the way out. So with all of the same things there for metrics and logs and making sure that those services don't have to worry about security themselves, they just trust that the network does that for them. We're able to also do things like dynamic routing. So we said before we want to send a certain percentage of queries to a new service. It doesn't know that it's happening at the service level, but we program the proxies to do that for us. All of this is done without having to make any changes to your application code. So you start off with a microservices architecture that's very simple. It just looks something like this. You describe in the standard format, perhaps of a Kubernetes deployment, this is what I want to have. And the cluster knows that it needs to deploy these proxies when you deploy these workloads. So it puts them in there like this. Again, we're still talking in the abstract here about service, what becomes a service mesh. So then, once you've got all of these proxies running along with your backends and an ingress proxy so that you can work on traffic from outside, how does it know what to do? Well, we already have a pattern for taking a lot of nodes and telling them what it is to do. And it's the Borg pattern, or what became the Kubernetes pattern. You have a control plane, you configure that control plane, and then it sends information out to a bunch of agents. That control plane will then program and maintain the proxies. So it will inform them all of the state of the services in your environment. So everything that's deployed, it tells each proxy server, for this particular service, here are the endpoints. So if it is doing round-robin load balancing, for example, it knows the things it needs to round-robin to. It doesn't need to call out to someone else to do that. It needs to teach the proxy servers where to send the metric information. So when it has requests and it reports back the latency and so on, it reports back tracing headers, it sends that to a central place, which is part of the control plane. Proxies enforce policy. So if you've enforced something about rate limiting or quotas or which users can access a particular service, you need to teach the proxies how to do that. So we do that with the control plane also. And then it also handles certificate provisioning and rotation so that we can encrypt the traffic between all of these services. Now, hopefully by now this will sound very familiar to you all. So first of all, if anyone remembers software-defined networking, anyone works at that layer, we've basically just reinvented that. But the difference is that we're doing it at layer 7. So we're able to make decisions based on application headers. We're able to say this traffic came in from a particular user whose name we know, or a device of a particular type. And we're able to say, here's a new service that we're testing, which is going to work for Android users. We're not testing on iPhone users today. So anyone who has a user agent that says Android, we can redirect their traffic. And that is only exposed to us in an HTTP header. We don't know just by looking at the network, looking at the packet and the bytes, what that is. And ultimately, it should be familiar because we're a couple of years now into the concept of a service mesh. So this is basically how we've done things internally. IBM had an open source project called Amalgamate, which was doing network routing. We talked to them and said, look, we're looking to do something in this space. And then we said, great, we'll work together. And so that is where we got to Istio. Now, I'm not going to do too much more of an overview of Istio because I already have. So everything you've seen so far, while it also describes our internal system at Google, it's a fairly good description of the things you can do with Istio. You install the control plane into your Kubernetes environment. You configure the cluster so that when you deploy a pod spec to it, it knows that it needs to deploy the sidecar proxy along with it. The proxy server that we use is called Envoy, which is a CNCF project. It was built initially by Lyft, the car ride-sharing company in San Francisco, for their microservices infrastructure. So it is purpose-built for this kind of thing. We built the control plane to configure it. And when you deploy that into your environment, you get all of that stuff before I mentioned pretty much for free. So I want to talk to you today about 3 customers that I've worked with, about why they have had problems that needed a solution like this and what they've found. The first company is called Descartes Labs. Descartes Labs are a reasonably new company. They're a spin-off of the Los Alamos National Laboratory in the USA, and they make machine learning models on Earth data. They get geospatial data, they get it from satellites, they get it from weather imagery, they look at light over time, and they combine all of these things together to get ideas of what's happening around the planet and how they can apply that predictively to other parts. They sell this information to forestry, to agriculture businesses, and they allow people to make predictions about things like global food supply and will there be political unrest in a particular region because of that. Descartes built their environment with microservices architecture. They built it on top of Kubernetes, running on GKE. And Tim told me a great story about their early deployment. He was out riding his mountain bike in the Sedona forest in the USA. And he got a text message that said someone had accidentally deleted all of their VMs. They'd just taken everything out. By the time he got back to have a look at it, Kubernetes GKE had recreated the VMs, and then Kubernetes had said the workload that you asked for isn't running, so it had recreated it, and everything came back up. That's exactly what Kubernetes is meant to do. That's why we're all here, because it solves that exact problem. So they've got an environment which is running great for them on Kubernetes, but it's running a little bit too well. It turns out sometimes it's a bit slow. Sometimes a call to one of their services takes longer than it should, but they don't know why. Now they have monitoring in their applications, so they've deployed things like Grafana and InfluxDB so that they can get metrics out of their particular services. But sometimes one of the microservices would just spike, and you know it has spiked, but you don't know why. The requests have just gone up. It's really hard to tell what it was that caused that. So by deploying Istio into their environment, they're now able to get metrics of the traffic between the services and find out who's calling who. And it turns out that they've made these microservices that are very, very useful to do certain things in their environment. They've scaled them for the size that they need for their production workloads. But other teams have said, oh, that's a useful microservice. I'm going to start calling that service as well. Or I'm going to send development test traffic to that service at a particular rate. And because they've sized everything for production, or they haven't thought to auto-scale this particular service, this one service is getting hammered, and that is therefore causing all of their users who are paying for the service to get a slow service. And so they're able to see visibility into the amount of traffic going to each service, very quickly identify this, and then auto-scale the service, or find out who's calling their service and say, hey, it's not designed for this, please don't do that. So it gave them an overview of the system and let them identify the areas that were trouble. Now they sell that service out to customers, and they want to be able to offer an SLA. So an SLA is basically a legal agreement that says if the software wasn't available for at least 99.5% of the time, then we give you back some money. In order to be able to do that, they need a couple of other things. They actually need to set their objective and say, well, we need to try and hit this. That's the 99.5 is what we call a service level objective, or an SLO. And then in order to know whether or not you've hit that, you need an indicator. You need a way of saying, what was it that succeeded or failed? And you need to understand the baseline performance. You say, this is how things work in the general case, so that you know when things are out of whack. If you want to be able to offer a service that is this reliable, you need to make sure all the services you depend on are that reliable or more. And you need to be able to know what your own target SLOs are in order to be able to offer one out to a customer. So being able to tell the amount of traffic going to each service, being able to see for this particular set of service calls or for traffic coming in from this particular user, this is what it has looked like over time. All of the requests that they've come in, we have been able to serve 98% of them this month. The others have returned 500 errors or something like that. You get all of this graphed for you automatically. The telemetry information is sent to the Istio mixer service, and then you can configure that to send it to Prometheus, to send it to stack driver monitoring, to InfluxDB, anything that you like. You configure that. You define what is acceptable for you and your business, how many errors are okay, whether latency is okay, or whether things have to return within a certain period. And then you can set alerting on this. You can say, I'm trending downwards. I know that 99.5% is 7 minutes per day that the service can be unavailable. So if you know that you're trending down for a particular day, you might say that's a problem, or you might define the service, generally SLOs are in like a 30 or a 28-day period. So you need to be able to be aware that you're trending downwards. In SRE, we flip that around and say that that's 7 minutes per day. That's called your error budget. That's how much you're allowed to be down. If you wanted to be down less than that, you should make your SLA higher. Your SLO higher, sorry. But that's a business choice because that costs more to do. So when you start eating up that error budget, you should be alerted, or a human at that point needs to do something. You need to come and figure out, and it might be manually scale something up until you've been able to look at the metrics and figure out what's going wrong. Now the other thing that Descartes have found is that they are taking new SREs, and they need to know what the environment looks like. You will probably have seen pictures of microservices architectures that someone drew in the documentation. This is one for a sample app that we have. And it's great, it says this should call that and this should call that and so on, but that was true at the time it was drawn, and because environments are always changing, it might not be true anymore. So you are able to draw based on the traffic that's actually flowing through your environment, either now or at a point in time in the past, because you have all this information stored in Prometheus. Something like this. This is a version of that same application deployed. This is in our stack driver service. But you can see what's calling what, and you can drill into each of those links, click on them, and find out what the number of requests per second are between them, and then go through and set those SLOs, for example. Another good tool for that is Kiali, which I think is being integrated with Istio to replace the default service mesh, but that was built by Red Hat, and it's an open source, again, a service graph that's looking at the default book info that comes with Istio there, but can draw these things here, not just for individual services, but for versions of the service that are defined within that. Descartes were one of the very early users of Istio. They were in the 0.2 timeframe, I said, so just a couple of months after Istio was released, they were running it in production. Another very early user of Istio are AutoTrader. They are based in Manchester in the United Kingdom. They're the most popular motoring website in the UK, the 12th most popular overall. They're actually a publicly traded company on the FTSE Stock Exchange. They were founded in 1975, and they used to publish a book of all the cars that were for sale that week. They published that book for 36 years, and then they retired it in 2013 when everyone had finally got on the internet. So this company was founded before the cloud. They have their own data centers, like everyone in that particular time. They have an app that's mostly written in Java. I have a personal story. I'm going to have to go, because we started a bit late, I'm going to have to go a little bit over time, but that should be okay because we're going into lunch. But I've only ever owned one car in my life. It was a 1993 Vauxhall Cavalier. Looks very much like that one there. I'm from New Zealand, and the second time I went to England was on holiday with some friends. It was going to cost £1,000 to rent a car for 3 weeks. So what I did is I went to AutoTrader and I bought a car. I bought it for £300, and I had to pay £150 to get car insurance for 3 weeks. And then at the end of that 3 weeks, I sold the car for £280. So all the rest of the time I've lived somewhere with trains. I didn't have to walk, but that's the one car I ever bought, and I bought it on AutoTrader. They have a website like this. They run a lot of different services for dealers and for car companies and so on, but as a user, you'll see something like this. But as I said before, there's a reviews section on the right-hand side. If I search for Vauxhall Cavaliers, they actually now cost £700. They're twice as much as they cost 10 years ago, and because people are trying to say they're a future classic. But if that review service doesn't load, that's okay. They can keep serving. But search is probably important, and the images service that shows you results is probably important. So AutoTrader, like many companies, have been looking at migrations and improving their efficiency. They've been looking at private cloud, but they found that they still had to deploy VMs and write code to talk to load balancers and so on. So they adopted Kubernetes so they didn't have to do any of that. After they chose Kubernetes, they had to decide where they wanted to run. And again, they don't want to have to worry about machinery, so they made the choice to move to cloud. So they have moved some services, again, to Google Kubernetes Engine. But they needed to make 3 migrations all at the same time. They needed to move to containers for Kubernetes. They had to move to cloud. And they also needed to upgrade their Java version at the time. So they thought that a great way to validate everything worked at the end of this would be using a service mesh. Now, around the same time, in Europe, we're working on this thing called the General Data Protection Regulation, GDPR, which means certain rules are required for businesses in terms of privacy. And it used to be that you'd just let people send encrypted traffic to the edge of your network, and then you'd just send clear text inside. It's not really good enough anymore with GDPR, so we need to be able to prove to regulators or so on that everything is secure. So they wanted to be able to deploy services and guarantee there was security all the way through. Now they have these Java applications. Java is not traditionally the best way to terminate TLS. You normally put some sort of sidecar in front of it. So they were looking at Nginx, or they were looking at the Boulder service, which powers Let's Encrypt. But then they would still have to write all their own code for certificate rotation. So this again was when Istio was announced. They were great. This will give us not only TLS and encryption, but it will give us mutual TLS, where we can validate the identity of both ends. And within one day, they were able to get something that they'd wanted for 3 months. By installing Istio in their test environment, they'd wanted that capability. It was great. Most of that work was done by 2 guys between Christmas and New Year's. So security was their first driver, observability was their second driver. So their test application, they actually found a memory leak in the application that they ran the major website for that had been running in production for a very long time. And they were able to go back and tell that team, actually, yeah, we found a problem that you don't normally see because maybe you just reboot the thing every day or something. But they've found now that they have teams coming to them, the cloud team, who are saying, we want to run our app in the cloud, not because it's cheaper or because it's more scalable, but because we think your tools are going to be able to help us find errors in our application better than our own tools. On the topic of pricing and so on, AutoTrader have built some great dashboards. AutoTrader have found that most of the information here comes from a tool called State Metrics, which you can take the information about limits and requests and so on from all of your applications and then store them in Prometheus. So they take the cost of an application, they take the amount of CPU it requests and multiply that by the price of a core hour on the cloud, and they're able to say, this is how much it costs to run each application. And then by connecting it with Istio, they're able to say, this is the traffic, this is the success rate of that application. If I lower those limits, I'm still succeeding. So they actually found they're able to drop how much CPU they're allocating to their applications while maintaining it still does what it wants. And they've cut their prices substantially as a result of this. Some of this is open source. There's a blog post, which I'll put a link to in the end. But they're showing dashboards like this to their customers. Some of the metrics come from Prometheus and from the applications. Some come from Istio, but they don't care. As far as the service owner is concerned, they're seeing a dashboard that relates to their service. It's not so much, here's an Istio dashboard, here's a Kubernetes dashboard, but they're able to merge these things together and say, this is your particular service. Final customer we want to talk about is Namely. They are 6 years old, so they're a little bit older than Descartes, but not as old as AutoTrader. And so they come from a world where they have these monolithic applications written in Ruby on Rails. They have, their company is doing HR software, so they have a service which is like Facebook for businesses, or an internal, maybe Weibo for businesses, and then a payments and payroll service. And these two applications both have their own data, but because they both deal with employee data, they have to have what they call magic, synchronize them. They have a service which links those two things together. And ultimately, they wanted to be able to decouple these things and get to a point where they were building fast and microservices environment and helping the developers focus only on their business logic. They knew that as they scaled the number of services from 2 to hundreds, generally with linear scaling, you would need to scale the number of people that you have also. You're one person supporting each service, you now go from 2 people to 100 people. So they wanted to scale sublinearly. They want to be able to automate, they want to be able to fight what we call toil in SRE, which is running repetitive tasks over and over again, things that are not particularly necessary. So to do that, they want to cut down that toil by making sure that every developer uses standard libraries, that they use the same RPC mechanism, and that they don't have to worry about things like authorization and authentication. That can just be done as boilerplate. So they adopted Istio. They put that on top of, again, their Kubernetes clusters, these ones running on Amazon. And they get metrics exported for free. You don't have to write boilerplate code to say, please send out these metrics. All of that stuff is done for you. It's sent out to their monitoring service. People would have to write the retry logic before. They'd have to write their own implementations with bugs in many different languages. It was toil, it was unnecessary, they got rid of it. If you call a service and the service says, hey, I'm overloaded, it gives you a 500 error, they've got a circuit breaker. So they say, we won't call that again for 10 minutes or so on. We'll let it calm down. We don't need to show those reviews if we don't have to, if we think that's going to be down. They can validate authentication. So they put the user's information, encrypt that into a JOT, and then each service all the way through, as part of Istio, can just validate that JOT. So you can configure it with the key that has signed it, and then each service in the Envoy, this is just straight out of the Istio docs, you configure a policy that says, take that key, check that it's still valid. If it's timed out, it's not valid, it returns a 500 error rather than returning a result from your service. Another very cool thing that Namely have done, used another CNCF project called Telepresence, which lets you substitute a two-way proxy server for a particular workload in a Kubernetes cluster that sends traffic back to a developer's laptop. And they use it like this. They have services that call each other in the cloud, but if a particular user wants to debug something, they configure it to say that when a request comes through with their user header, instead of the traffic being routed to service B, it gets routed to service B prime, which is a telepresence pod, which sends it back to the developer's laptop over the tunnel. Then they're able to attach the debugger to their local version of this, and they're able to debug that themselves without having to do anything complicated running on the cloud. And Istio's traffic routing makes that possible. Just wrapping up very quickly, you can adopt Istio in pieces. My colleague Dan likes to call it Istio a la carte. The three main things that we see as people taking as a benefit out of Istio are traffic control, being able to do canary deployments and routing people for various versions, telepresence and so on, the observability, and then the security you get from applying mutual TLS. If you want to know what's going on in your environment, deploy the sidecars, deploy Mixer, see what's happening, but don't configure any policy, don't do security. Things might break if you put TLS into your environment, so you don't want to do that unless you're able to validate it. If you're worried about only traffic coming from the inside, so we have customers where they don't have any service-to-service traffic. They host for many different customers. They host one pod per customer. All their traffic comes from the internet to that pod. If pod A talks to pod B, that's wrong. It shouldn't ever happen. So they only run the Istio ingress, and they don't run the sidecars. They use it just as a way of programming the Envoy. And we've seen people, especially in financial services, who have built their networks to say, I have a certain number of IPs in this range and a certain number of IPs here, and if you're in this, you can call to that. And then when they find that they've got spare IPs over here, but they don't have any in this, they've built their network based on you have to be in this place. It's better to do it with an application identity, to be able to say, my app knows who I am, so therefore I don't need to worry about shaping my network. You can run a flat network and move the security to your application layer. So 2 pieces of advice with Istio: start small, find the piece that works for you, and then apply that. We are working in the project to make it possible to deploy it in parts, so if with a Helm installation, you just install the pieces that make sense for you. If you don't need security, don't install security. My second piece of advice is you should listen to the Kubernetes podcast, which I co-host with my friend Adam, who I was around before. I don't see him now. But I've seen at least a few stickers in the audience, so thank you very much for those of you who have gone and got them. But you can just throw that into your podcast player or go to kubernetespodcast.com if you enjoy listening to me talk. And with that, that's the end of my presentation. Thank you very much. I'll be around if anyone has any questions. All right, let's come up the front, I think, because they want to move on with the room. Sure.